Hi everybody, welcome to the Stories lecture about techno-economic considerations on hybrid storage for mobile applications. Basically, what I'm going to tell you in the next couple of minutes is valued for all kind of techno-economic considerations, techno-economic analysis, but I will be focusing more on mobile applications when it comes to examples at the end. So let's start right into it. What are techno-economic analysis? Well, let's get into it with a definition. Basically, the definition is it is a comprehensive evaluation methodology for analyzing feasibility, cost effectiveness, and performance of energy technologies or systems. What do we mean by that? There are key components. There's a technical analysis and an economic analysis, and then there are lots of components typically when you do such kind of analysis. More than one, basically, otherwise it would be quite simple. And very often it's generation, it's consumption, and it's maybe also storage in that. That's most of the time when we do techno-economic analysis in the energy sector. The objective is that we want to be able to make informed decisions on which technology to invest, how large different components should be built, and we want to have a fair comparison between different technologies, between different systems, between different setups. Yeah. And also, dependent on what you're analyzing, might be supplementary analysis, something like sensitivity analysis or risk analysis, if you want to know if you tweak certain things, how do your results change? That would be a sensitivity analysis, for example. Okay, there are different study formats that you can divide your techno-economical analysis into. Very straightforward one is the technology feasibility and viability, where you just make a study and check whether this technology or this project or whatever you're evaluating does make sense from a technical point of view, if it even works, or if it's not technically viable at all. And also if there are some technical economic barriers that hinder it, right? Another thing would be, if you're more or less certain that it is viable, you can go into design choices and go into your design parameters. So this would be something, for example, you have a storage system and you want to know how large should I build this storage system in order to make sense, or how large do I want to build some different components in there, because typically larger components are more expensive, but then also they produce more. So this trade-off, techno-economic analysis. Technology comparison, you have one or the other technology in there. Which one does make more sense from an economic point of view? Could also be other key performance indicators, KPIs. For example, could be CO2 emissions or something like this. Future technology projection, if you basically want to have some, maybe also technology feasibility of future technologies, or just compare some technologies that are not yet in the market, but you model them in a techno-economic analysis and see if it would make sense to proceed into this direction in the future, right? And maybe also what impacts this would make on market prices or something like this. Similar things, research and development needs, quite similar to the last one, because also there you're basically looking into technologies that are not yet on the market and have a look, okay, so where do the research roadmaps, what should be included into the research roadmaps, which technologies, because they would make sense in the future. And replicability and scalability, very important one actually, because not every technology makes sense in every region, right? So just imagine, for example, hydrogen production coupled with PV, with photovoltaics. You have much more full load hours somewhere in Spain, for example, that you would have in the north in Norway, something like this. There would be very different results. So replicability, scalability, yeah, very important thing when you do techno-economic analysis. Okay, so how do such simulations work in the back end when we are doing such things? So when we are doing such things at AIT, we have a framework here, and we feed this framework with all kinds of data. And I always like to highlight that this data that we feed in is profile based. So we are not only working with yearly sums of energy consumption, but we typically have 15 minutes profiles of everything that we're simulating. Why 15 minutes? Because this is the billing period in electricity, basically. Yeah, so, but we need profiles, of course. So load profiles, generation profiles, and also market data. If profiles are available, would be great, because they are also prices are varying quite a bit. And yeah, also feed in some other economic and model parameters, and this will be your scenario. There can be very many different scenarios, should be very many different scenarios when doing a techno-economic analysis, but this is what defines your scenario here, those input data. From this scenario, you build your components, so all the components that you have in this scenario, and you also have an operational strategy. What do we mean by that? So, for example, taking maybe what is depicted here, you basically have a house and that's powered by some renewable energy, and you have a battery storage in this house. Then different operational strategies might be you wanna operate your battery in the way that you earn money with it. So sell to the grid at when you get the highest feed-in tariffs, or on the other hand, maybe you want to maximize the self-consumption. So consume as many of your renewable energies that you produce yourself, storing the battery for later consumption. But this is maybe a different thing, and is not what is economically the best one. Might be. Okay. Nevertheless, you have an operational strategy that defines what you are doing in each time step, and this feeds back to the component model, and so on and so forth, and sets what is happening in your simulation at each time step for the one scenario that we are currently simulating. Then there is a technical assessment and an economic assessment when the simulation is through. And you also, dependent on your use case, maybe you want to have an optimization, because maybe you want to know, does it get better if my battery gets larger or smaller? And this would then be fed back to a scenario definition, and then you do the same with another scenario, maybe with a larger or smaller battery, with a larger or smaller PV. Maybe also with a slightly different operational strategy, whatever you like, but yeah, so these are things that you can do in there. Very important, which we should not forget, is results presentation. So yeah, because you always need to present your results in a way that people will understand what you're presenting, more or less clear. But for the techno-economic analysis, you need to get the message across, because otherwise people won't see what you have been simulating all the time. So how could this look like? I'll give you a short example on how this could look like, right? So since we have lots of profiles in there, this energy and power values of the profiles could make sense. So show all those profiles that went in or that go out of the simulation. And your most important key performance indicators. We'll get to this in a second. So there are some slides on all those key performance indicators later on. And there are some for the system and for the components themselves too. And important, of course, is if you change the parameters, so sizes of a component, something like this, then your KPIs is also how you measure your results for the different results there, right? Okay, and just to give you one example how this could look like, this is a generation profile of PV, and you see that of course the generation is lower in winter than in summer, but actually it was highest in April here, interestingly. And also, not very surprisingly, your PV generates electricity, generates power during the day and not during the night. Well, okay, yeah, but this is some kind of nice visualization that you could do that would make a lot of sense. And then, okay, so this is a little bit hidden behind me here, but I think I can talk you through here. So some heat maps are always also some good idea, for example. So what you see here is, I think at least it should be different sizes of storage. So I think a battery storage and different sizes of the converter, AC-DC converter for the battery. And there you can see which levelized cost of electricity comes out when combining those two different sizes of the battery and the converter. And you see that it gets lower and lower the larger the battery and the converter is, basically in this example. Yeah. Okay. So as I said before, KPIs. Yeah. So there's gonna be some text on the next slides, but bear with me, then I'll get to some examples later on. But now we have to go through some text now. So what kinds of KPIs do we know? So there are technical KPIs. Technical KPIs, for example, energy demand, energy consumption, and supply rate. I think they are more or less clear. I don't have to go much into detail for them. Then there is grid consumption and grid feed-in. Yeah. Dependent, for example, as I said before, on your operational strategy, maybe if you have some storage, right? And there is energy curtailment. That's also something that's always at least asked for in those techno-economic analysis, because people always are very interested if they so example for that, you have a wind farm, a larger wind farm, and the grid operator does not allow for the whole peak performance of the wind farm to be connected to the grid. That's very typical. That happens all the time, and therefore could be one example that you should do a techno-economic analysis and have a look if a battery would make sense there for or not. If you don't have any storage, then you just have energy curtailment when your wind farm produces more energy than can be fed into the grid at a certain point. Also, when you have the storage in place, then there can also be some energy curtailment if it's just more curtailment than your converter for the battery is able to feed into the battery currently, right? Yeah, but energy curtailment, people tend to want to know how much energy they throw away. Basically, this would be energy curtailment. And then there's self-sufficiency and self-consumption, also some technical KPIs. So self-sufficiency is how much energy you are able to generate yourself on site. So 100% self-sufficiency is basically autarky, right? And self-consumption is the percentage, so how much of the energy that you generate do you consume yourself? But this can also mean that you still have to take something from the grid, but yeah, even if you consume all that you produce on site, if it's not sufficient, then you still have to take something from the grid. I think that's more or less clear, I hope. Yeah. Okay, then efficiency. Yeah, you always have to be careful how to define this efficiency for your different components, but I think it's more or less clear what efficiency means in this context. State of charge. This is an interesting one. So because state of charge is something that makes a whole lot of sense for a battery. It's quite clear, everybody knows state of charge. You know state of charge from your mobile phone, right? So clear. Yeah. State of charge can become a little tricky, for example, when we are talking about a heat storage system. Just think of your heat storage that's standing in this, so heat water storage that you need when taking a shower, something that's standing in the cellar, in your cellar, maybe. So there might be an upper limit for the temperature, that's quite clear, but what's the lower limit for this temperature? Is it lower than the ambient temperature? And what does this mean? Where is your zero state of charge for this one? So state of charge might not be straightforward depending on what kind of storage system you're looking at. That's what I want to say here, right? Full cycles. More or less same thing, because for battery, quite clear, full cycles, right? So when you go from 0 to 100 and back again, this would be a full cycle. For the heat storage system, not so straightforward again, right? Operating hours is more or less clear, I would say. And then state of health and end of life, they are also very important for your techno-economic analysis, because well, when the state of health reaches a certain point that you defined as your end of life of the component, then you have to replace it. When you have to replace it, you have to reinvest. So very important thing, because this is expensive, very expensive, potentially. So good aging models for the different components, good degradation models are quite important for the techno-economic analysis in order to project your state of health over longer times. Okay, then let's get to the economic part of the whole thing, cash flow components. So basically you can break down everything to capex and opex costs. Maybe you've heard about that before. So capex is everything that you need to invest to have your system standing there before getting into operation, and reinvests what we had before. If the state of life, so if you reach the end of life and you have to reinvest, that's also a capex, right? But that's basically everything that's that you have to invest without having it operating, right? And then there's the opex cost. That's everything that comes with operation. We'll have some example shortly for all of those things. And then there are some things that can be either or, for example, financing costs, maybe more capex costs, but well, depends what you, could also be some opex. Land and permitting costs. If you buy the land, it's more capex. If you rent it, it's more opex, right? Environmental compliance costs, transmission grid connections costs, so something like grid fees, which are also a very important part typically when simulating larger systems. And reserve funds, so something that you have to set aside for unforeseen events or something like this. I've never used this so far in a techno-economic analysis, to be honest. So what else? Revenues, because we want to make money with the system. At least we hope so. So where can you make money with? Of course, you can sell for example, the electricity that you have, right? As we said before. So definitely. Certificates of origin, that would be CO2 certificates, for example, something like this. Feed-in tariffs. When you feed your electricity to the grid. Selling surplus energy. More or less the same again when thinking of electricity, but you can think of more, for example, think of an electrolyzer, for example, that's producing hydrogen on the one hand, and it produces heat. So if you are able to also sell this heat to somebody who needs it, for example, I don't know, maybe a district heating network or something like this, that would be also selling surplus energy. So don't only think about electricity here, right? And yeah, ancillary services, something that we've been looking into more and more in the past years, when you do frequency reserve, grid stability, so providing services for grid stability, for example, and making money out of that. Yeah. So just to give you some more example on what kind of other OPEX costs could there be in operation. So yeah, you might have fuel costs. I'm not gonna read all of them, but for testing and monitoring, security costs, administrative costs, name it, there can be, and the list is not complete, of course, but just to give you some examples what it could be here, some OPEX costs. And then also the most important KPIs on the economic side. Don't worry, I always have to look them up myself too, because I'm not an economic. But there is the net present value. That's one of the most important ones. That gives you the information if your project is going to be profitable, if there's going to be a profit from your project or not. And this is the net present value. And then there is the return of investment that tells you how much of the investment will get back, basically, right? So how much you will get back. And then there is a third one, and this is the internal rate of return. That's for me, that was always a little bit difficult to understand at the beginning, but you can imagine it that way, that it is for the companies. They don't want to just make profit out of it, but they have a kind of hurdle where they say we want to make at least a couple of % per year profit of it. If we make less than that, it's not interesting for us. And this is this hurdle rate, and therefore it's kind of a little bit stricter maybe than than just the return of investment. I hope that's okay. I hope that's right, like this. Otherwise, some economic, please correct me if I'm wrong here. And then I think the payback period and the amortization time, I think that's more or less clear. And one very important thing is, of course, the levelized cost of energy. So what kind of energy you have, could be electricity, could be heat, could be hydrogen, whatever you're doing. So the minimum price you need to sell your energy in order to break even. this is the levelized cost of energy, a very important one. Okay, so last one for this more dry, more theoretical ones. But if you ask me, very important one is the level of detail for this techno-economic analysis. Why? Because typically you don't have all your input data in the same granularity. But you want to be consistent, because it does not make sense to model one of the components very in detail if you have huge uncertainties for another component, right? And also you want to balance between the complexity of your results and the actual question that you want to answer, because also if the question does not require that level of detail, you also don't really need it, right? Typically, you are limited by the data availability, as I said before, or the computational power when you go much more into detail. But mainly, from my experience, it's data availability where at least one of your component is not available in maybe that granularity than other ones. The theoretical optimum would be that, of course, you have similar level of detail for each technical component or each cost component in there. Difficult in the real world. And as I said before, different research questions require different levels of detail. So don't go too much into detail when your research question is not that detailed, actually. And also don't do the other way around, of course. So, as I promised, examples, so that you get a little bit of an overview what we do as techno-economic analysis. It's quite broad. You can do lots of things, and I also named some examples already in the past minutes. But I brought 3 of them, and they are now more focused on transport, on mobility. The first one was a study that we did for the Austrian lake shipping, actually. So what was the question? The question was that the ships that are currently traveling on those lakes, there are also for passengers, also for leisure, but yeah, a little bit of both. And they run on diesel at the moment, right? So just fuel based. And the question was, does it make sense to refurbish them to hydrogen, to make them hydrogen propelled? So what did we have to do there? So we had to model the complete hydrogen generation chain, and also have a look on the schedules of the ships, because it is the question, how often do they have to be refueled, which is different on the Wörthersee, which is a smaller lake in Carinthia, than on the Bodensee, which is one of the larger ones, and they tend to have, of course, larger legs when traveling there. And yeah, so also something that you had to do there. And then you have to model the components. What are the components? The components are your electrolyzer, your storage system, also some compression, and also compare it with the possibility of just buying it from somewhere else, just so then you don't need all the components on site, but yeah, you have to buy the much more. You need a storage anyway, yeah, that you would need, but you don't need an electrolyzer or something like this. And And there you have, okay, this is partly in German. I hope this is okay for you, but it is electricity costs, it is the converter, it is the electrolyzer, capex and opex, and also converter again, and yeah, some additional capex that you just need for getting all the auxiliary systems and something like this in place. And then there was the question, it's a little bit behind me again, but I will talk you through. The question is, how expensive is it, levelized cost of hydrogen, as we discussed before. So what's your minimum hydrogen price per kilogram when doing all those things, and how does it so which component is responsible for which amount of this hydrogen price. And the question was also if you have different storage systems here. So, and you see that, for example, the 350 bar storage system is better than the 700 bar storage system, and this with the asterisk here is taking into account some additional funds. The right-hand side, that's a little bit hidden behind me here, is when buying it from some external source. So in this case, the analysis showed that actually, well, it showed two things. It showed that it would be cheaper to really produce the hydrogen actually yourself than just to buy it and to ship it, because transport it to your fueling station, because this is what's very expensive too. So yeah, that producing it on site would make more sense, would be cheaper, but that's not cheap, so it's expensive anyway. So that's the main takeaway. It's still expensive. And yeah, okay, so much for this example. Second example that I brought you. The Austrian ministry, wanted to have a hydrogen import study. We did this together with Frontier Economics. They did also a large part in this study. And the key question was, in the future, when Austria might be importing hydrogen, how could we do that? So with how we mean, so which transport medium. So you could, for example, as you see here, you could go to ammonia, you could have some, those are those liquid transport liquids where hydrogen is stored in them. Yeah, different things, pipelines, and okay, so different transport options, let's put it like this, and different regions where it could origin, for example. So even Chile, very cheap one, because Chile has a lot of full load hours in wind, so you could produce hydrogen quite cheaply in Chile. But then you have to transport it somehow to Austria, which you could do by ship, but of course not all the way, because there is no shore in Austria. So you could transport it, I don't know, to Rotterdam or something, and then you still have to transport it to Austria. So, but yeah, that are kind of the challenges that were, yeah, in this study. Okay, so what did we do here? So these were different generation regions that have also some, different shares of wind and PV, dependent on the region. And then there was the question how to transport it here. And some main takeaways from this study were that, for example, as you see, producing in Chile is quite cheap, but shipping here is then another thing. And the question when shipping here is, for example, okay, so you have to, so somehow compress it or somehow transform it to some other thing. As I said before, for example, ammonium would be quite promising, but actually you need ammonium, for example, for your fertilizer production or something like this. So actually, if you have this already, you would not really transform it back. So yeah, so this would make a whole lot of sense to produce it in Chile, make your ammonia, transport it here. This is something that would make sense. On the other hand, as you can see down here, the pipeline is always cheaper than all kind of shipping options. Of course, Chile is out of the discussion then, because we want to build a pipeline to Chile, but we're talking more about the Northern African region here, right? Pipeline was taken into account with all the fees that you need to pay when using it, and so this would also be some takeaway from this study, that the pipeline from Spain, of course, also from Tunisia or something, is just way cheaper than all kind of options when you're shipping it by ship. Yeah, I think that is more or less the takeaway that I would say we could take from this study. Okay, last example that I brought you is a study that we did for FOR. So FOR is a mobility provider in the eastern region, so Vienna and surroundings region in Austria, and they also wanted to know. They also have some fuel-based buses at the moment, and they wanted to know, does it make sense to have them, well, also either electric buses, battery-based, and but here we were also here. So this one is more focusing on the hydrogen buses again. So hydrogen buses, right? And there are different kinds of things that we had to look at. For example, okay, so how do we produce this hydrogen, or how do we get the hydrogen? So more or less same thing as for the ships again. Either you take it from the grid, or you take it from the renewables, or maybe you buy it just from somewhere else all the way, right? And then to get to your fueling station for the buses. And also there again, you had to have a look at the schedules of the buses, where it makes sense to refuel them, and which buses would make sense to have them hydrogen fueled, and which make more sense to have them have battery buses. And interestingly here, one of the results was that some of the routes are really not, at least currently, not really feasible for electric buses, because they're just too long, and there would make sense to have hydrogen ones. But there are also lots of buses also in the south of Vienna where it makes sense to have electric buses, for example. So there we are in the technology comparison, as we had for different simulation studies, right? Yeah. Okay, so those were basically the 3 examples that I wanted to show you for the mobility, and I gave you some others during the presentation. And I think that is a nice overview about how techno-economic analysis work, what we are doing at ART for techno-economic analysis, and yeah, so in a real-life settings, I would take questions now, but yeah, if you have questions, here is my mail address, so mail me. And yeah, thanks and have a nice day.